Hi, welcome to problem 6b. For 6b, what's important is you shouldn't really read into the story too much. You just need to know what you're being asked for. So, assuming that we don't have corruption in A, so all these preferences are set, we need to know which two preferences can be switched. So, obviously you can't switch these preferences here because the information in A is not corrupted, so the only places you can switch are these question marks here. And think about why you can get away with switching them while having a stable pairing. So remember from our discussion that 2 and B and 2 are first, so on day 1, 2 and B meet and will be together forever. So that's why the preferences for 2 don't matter and can be switched arbitrarily. So we also notice that since 3 and C are part of a stable pairing, uh, 3 never gets rejected by C. And since C is 3's first choice, we know that 3 never has to propose to anyone else. So 3 doesn't have to propose anyone else. And so this means that the preferences for 3 don't matter. And for C never sees anyone better. And so that's why the preferences for C don't matter. Well, I'm saying the question marks. So you can switch any of those preferences and they will not affect the stable marriage algorithm. Excellent. Let's move on to part C. Hi, welcome to problem 6C and 6D. 6D is actually easier, so let's go through 6D first. Here we have a hyper-intelligent adversary who wants to do the most damage, but you want to find the least number of root pairs that will be generated, which is sort of like damage control in a way. So, therefore, we should think of extremes here with the least. So, think extremes leads to think of how algorithm can be exploited. And an important note about the stable marriage algorithm is that it's male optimal and female pessimal. Now let's consider what root pairs refer to specifically. So as you can recall, for root pairs, you need the man preferring a random woman star over W, where W is paired with the man, and woman prefers man star over M, where M is paired with the woman. And you can think of this man as man star and this woman as woman star. So this is what root pairs are. And how do we generate them? Well, how does the algorithm affect root pairs? Well, if you think about it, this algorithm is female pessimal, so does the algorithm really have a say about case 2? Actually, it really doesn't. It depends on the proposals the woman receives. So the algorithm doesn't really have control over case 2, so not really affected by the tweaking of the algorithm. So let's just consider case 1 here, where man prefers woman star over woman. So recall how the algorithm works. So on day 1, every man visits his most preferred. Let me get rid of that. So the only way to take advantage of this is to end the algorithm early. So if you end the algorithm sooner, every man will get the person he prefers more. So strategy, end the algorithm sooner. We're taking advantage of this strategy, this part of the algorithm here, where you don't want a lot of people to be rejected. Now take that to the extreme. What do you have? You have that, recall from problem 6a, where you had 2 liking B as the very first choice, and B having 2 as her very first choice. So on day 1, these 2 people get matched, so no rejection. Now repeat this for all the other couples. So 1A1, 3C, C3, and no one gets rejected. So if everyone is matched first, is matched on day 1, there are no root couples. Everyone gets their first choice. And algorithm is terminated early. Is terminated early. So we need to use this to our advantage. Now, the part of the problem that might present some difficulty is proving this. So let's actually prove it. So here we have suppose, and you want to talk in general terms as much as possible in a proof. So suppose you have a man, W. Well, before that, suppose every man and woman have a soulmate. The person he and only she or he matches with on the first day. So this pretty much describes the phenomenon where you have B2 and 2B. So everyone gets matched and there aren't any collisions. Now, suppose the adversary attacks. So now we have a man, M star, whose preferences are switched. Then everyone but man star gets matched with soulmates. And since there are n-1, so everyone equals n-1 men, get matched with soulmates, then n-1 women are matched, which leaving out woman star. So M star and woman star get matched on day 2. How many root couples are there? Well, if you think about it, all men prefer their mate, except M star, of course, prefer their mate over W star, or else they would have proposed to M star, to W star, sorry. So then this leaves out M star. Who does M star prefer? Well, M star prefers someone other than W star, or else he would have proposed to her first on day 1. Based on that, so based on everything, the only root pair candidate is M star W star. But W star would, but W star's preferences are the same as before the adversary attacked, right? Before attack. So W star prefers M star over any other man. So no Rug couple either here. So no Rug in this case. Which means that in general, there are no Rug couples for this pairing after the attack. So for a pairing where every man and woman have a soulmate. That solves problem 60, so 0. This is problem 6c. The problem asks us to find how many Rug pairs could be generated, so potentially an upper bound, by an adversary for any arbitrary stable marriage instance, which is just a preference lists for both men and women. So we should first consider the question of how Rug pairs are generated. And from our discussion in 6D, we have the man has to long for woman W star over current W, who he's paired with right now, and the woman, this is an and relation, longs for man M star over current M. So generally the algorithm gives us great control over the men, but we'll see in a few moments that it doesn't really matter which relation you look first. But let's just first picture the men for a moment. How do we get these men to long for a woman? Like, how do we guarantee that to happen? Well, one easy way is for all the men to long for the same woman. And now, based on the setup of this problem, the woman can only choose one man. So the woman will reject the n-1 men and will keep the one that she, on paper, likes the best. Now notice that all these men long for her, so if for some reason this relationship is not quite right, then suddenly you have instability in your environment. And so this relationship between the woman and the man she ends up choosing must be mutual, or else she'll long for any other man, and of course all the men already long for her. So this is actually a weakness that the adversary can exploit. And so hopefully this example captures some of the intuition to the problem. Note that our strategy was to bring an example to the extreme. So extreme example, where everyone is paired to one person, prefers one person. Good. So this shows that one person's change in preference, so if we change this preference, then all of a sudden we can generate as much as n-1 Rug pairs, couples. But on the other hand, with this extreme example, which helps make this question look more polar and less wishy-washy, we can see that this woman must participate in all of the Rug couples. So we have to prove this, though, and so this is the next step of our solution. So as with all stable marriage problems, it is a good idea to first talk in general terms. So we want an M to refer to all men, while M star refers to a special man. And M is for a normal man. And now in this case, M star will be the person with the preferences switched. Because this is what the special thing that is going on in this problem. So now The second helpful thing for stable marriage problems is proof by contradiction. Here, we assume that for contradiction, toward contradiction, that M can form a root couple. Why do we make this assumption? Because in our previous example, we saw that intuitively the person whose preference is switched is the one that must be in all the root couples. And the extreme example is extremely clear, so we can see, we can hopefully capture some of that intuition here. And of course, sometimes these intuitions can lead to a dead end, but other times they can help solve the problem. So let's just test it out. So suppose then that M prefers woman star over the W that he is currently with. Okay? And so M must have proposed to W star, but got rejected. Why? Well, so then each man goes off to the first woman on his list, and if it's true that for M, W star is more preferred than W, then W star is further in front of the list, farther in front. And this is the same notation I used for the previous parts of this problem. So then M must have proposed to W star because nowhere in this algorithm does it say that the man goes out of order. So, or else, of course, M, W star would have been paired together. So, by virtue of W star rejecting the man, W star must have found someone greater than or more preferred than M by the improvement lemma. Now, the improvement lemma is something similar to a greater or equal to, like you can stay with the man or you can find someone better, but we already proved that a W star did not stay with M, or else this pairing would have existed instead of plain W. So good. So this means that no woman longs for M more than his current partner assigned by the algorithm. Therefore, the conditions for a root couple are never fulfilled. And this is, of course, a contradiction to our original assumption that you can form a root couple. So, contradiction. And so this means that only M star can form root couples. And how many root couples can M star form? Well, obviously, M star is paired with his most optimal woman, W star, for instance. Yeah, and so then this W star is actually not the same, but as this W star here, but whatever. So then, apart from the most optimal one, there are n-1 women that are candidates for being the other end of the root couple. So that's where we get the n-1 from. And I'll give you a second to copy this down. Please pause now. Okay. Now the intuition is similar for women. The key is that when all men propose to the same woman. Propose to same woman. Let me just draw it out here really quickly. The woman is immediately paired. So we have A, B, C, or B, A, C, reordered. And following from our previous example, immediately paired with the first man on her preferences. So switch this with the worst preference, best, worst, and all of a sudden you have CAB. The woman is paired with C, her least favorite, should much rather go with A or go with B. So woman would much rather go with A or B. So the women will form root couples. And how many of them? The same as last time when we proved this for the men. N-1 root couples that are not her last preference, right? And so therefore, for any arbitrary stable marriage problem, an upper bound of 1 minus overall couples can be generated. And hopefully this walkthrough showed you some of the intuitions that arise from the application of this algorithm. Excellent, and so let's now move on to problem 7.